the thing is that, for example, if you have two variables, how do you envision these two ones here? Oh, sorry, this is normal. Forgot the normal here. So remember that this tilde here implies is distributed as is distributed as a normal distribution, as a t distribution, whatever distribution you can imagine. Okay, so when we talk about the normal distribution, guys, how do you distinguish these two guys here? If I graph them, I know that the mean of both of them is 10, correct? Now, which one do you envision is going to be thinner? Which one is going to be fatter? Which one, guys?
The 6 would be thinner.
This one?
Yeah.
What do you think? Another opinion? Remember, guys, the standard deviation is how dispersed the data is. Got it? So indeed, how dispersed, so imagine that what I envision, this one here has a lower dispersion than something like that. Correct or not? So these are values. Do you agree with me or not? Dispersed with respect to what? To the mean. The black dots are less dispersed than the red dots. Agree with me? So the black dots, guys, should represent a lower standard deviation versus the red dots that should represent a higher standard deviation. So indeed, Paul, is the opposite. Okay, the smaller the standard deviation, the thinner the distribution. The larger the standard deviation, the wider the distribution. Okay, so basically my 10-2 should be perhaps something like that. Very thin. It should be, of course, guys, it should be symmetric, okay? I don't know, even one symmetric. And so this should be 1. So this should be x1. X1. And the other one should be something like that. So this should be x2. Make sense? The more the dispersion, the wider the distribution. Less peaked, wider and wider. Right? So you just imagine with these two parameters, guys, you can imagine everything. Questions, guys? So we can do a couple of examples because before going to there. Let's define, guys, a C variable. Okay, the C variable is what is called the standardized variable. The C is simply, CI is simply going to be to xi, let's call it minus mu over sigma. Okay, so you have every observation, you subtract the mean, divide by the standard deviation. And what is interesting, guys, is that the expected value or the mean of CI is always going to be equal to 0, always. And the variance of CI is always going to be equal to 1. So if the variance is 1, also the standard deviation is going to be equal to 1. Okay, so these two properties are crucial, guys, because it's going to help us understand a lot of statistics. Do you see my screen? You see my Excel? So let's create one variable X, anything. Okay, 12, 3, for example, anything. Okay, anything. What I will do is I will compute the mean and I will compute the standard deviation. So the mean is average. So I compute simply the average here. And I will compute the standard deviation. So let's assume this is a population. So we can do that. The standard deviation population. Okay. Got it? So this is my mean, my mu, and my standard deviation sigma. How do I define the variable z? C equals every single number. This, I'm sorry, what I'm doing is this number, every single xi minus its mean, so F4, just to fix it, divided by the standard deviation F4, fixed. So I need to put parentheses here. Do you see what I'm doing, guys? I'm building my Z, correct? So if you take a look, so these are the Z values. If you see, guys, the Z are simply transformations of X. What is beautiful, guys, is that if you apply the same standard deviation and mean, take a look, what is the mean of Z? 0. What is the standard deviation of Z? 1. Always. It doesn't matter what numbers do you have here. As soon as you build your Z, as I wrote before, the mean is always going to be 0, and the variance and the standard deviation is going to be equal to 1. Always. Right? So that's why it's called a standardized variable. It's clear to everyone? Do you believe me? C always have 0 and 1. Okay, so let's go back to this part here. So, and the other property, guys, that is extremely crucial is the following. If X is normally distributed with parameters mu and sigma, then Z, that is equal to X minus mu over sigma, is going to be a normal 0, 1. Do you agree with me? Because the mean of Z is always 0, and the standard deviation of Z is equal to 1. So you can transform, guys, any series that are normally distributed, well, in this example, transforming to X into Z and obtaining normal distributions 0, 1. Okay? So let's do a couple of examples so you understand what I'm doing. Oh, 1 more minute to copy, guys. Perhaps you didn't copy.
Sorry, Professor, can you go back to the last part? What you said, so if X is a normal distribution.
Parameter mean is mu, and standard deviation sigma.
Yeah, so Z.
C that you build is X minus mu over sigma. So what we have done, like in Excel, is always going to be a normal distribution, normally distributed with parameters 0 and 1, always. Because you know what is the mean of C? 0. What is the mean? The variance is 1. Right? Always. Yeah. Okay, so you're gonna, it will make sense in a minute with one example. So imagine the following, guys. Imagine the following example. So imagine that you know, okay, let's do one example. So let's assume that you know that X is normal, for example, 85, 2. Okay, so these are the grades. So imagine that this is the average grades of global financial market students during all these years, 85. and the standard deviation is equal to 2. Right? So you know that. Now put this in perspective. What is the so you're going to be always trying to understand, you know what, if I select one individual randomly that took the class, and I ask this guy, okay, what was your grade? Right? So that's my experiment. What I want to know is, what is the probability that this number, for example, is going to be equal to 86? Okay? So here's a trick. Remember, guys, that the normal distribution is a continuous distribution. Do you agree? So it means that every possible value is possible, it's feasible. What I'm asking to you is, okay, so this number here is 85, that's the mean. What I'm telling to you is, I want to know what is the probability of having 86 sharp. Now, a probability, guys, indeed is estimated simply as number of successes divided by total number of results. Now, in how many ways you can get 86 sharp? How many ways?
0.
No, 1. 86, you can get 86 only in one way, 86. Agree? How many potential grades you can have? If it's continuous, this is going to be infinite. You agree? So what is this number then? 1 divided by infinite equals what, or approaches what?
0.
0.
0.
Exactly. So that's why, guys, when we talk about continuous distribution, we never ask equalities. We never ask what is the probability of x equals a number. What we need to do is we always need to we need to construct intervals. Got it? So this is one case that, you know, please, if you have a a continuous distribution, a question like that, it is always here. Now let's do something more realistic. I can ask, what is the probability that this individual that I select randomly will have a grade smaller than 84, for example? Let's do this with me, and then you do more exercises, okay? Just follow me for a minute, guys, and then you copy, and then you do exercises. So let's do this by steps, okay? So my step number 1 is going to be create the C values. So what I will do is I will transform this one into Z. So this is going to be x minus mu over sigma, correct? Agree? So what I do is 84. What I do in the right-hand side, I do in the left-hand side, I do in the right-hand side. So this is going to be 84. What is mu according to my data? 85 divided by my standard deviation, 2. Agree? So this is going to be equal to the probability of Z, because this is C, larger or equal than, this is -1, minus 0.5. You agree with me, guys? Please, first, follow me, and then you're going to have time to copy and more exercises. Okay, once I have the Z, my step 2 is going to be graph. Okay, so how do I graph?
I'm sorry,
graph?
Prof.
Yes, go ahead.
Shouldn't the inequality sign be the other way around?
Ah, completely right. I don't change anything. I cannot change my equation. Inequality in this case. If I'm asking for a smaller or equal, this is going to be a smaller or equal. Got it? Now remember, guys, that this one here is now in terms of Z. What is the mean of Z always? 0. So what I'm requesting you here is the probability of C is smaller than minus 0.5. So what I will do is I will find here minus 0.5. And what region I'm looking for? I'm going to be looking for this region here. Do you agree with me or not? This is the probability of C is smaller than minus 0.5. Correct? What is your step 3? Well, Excel. Okay, so let's do it in Excel. Just follow me, please. Let me do this. Okay, let me create another one. So what I will do in Excel, guys, is I will write here my minus 0.5, the number that I'm looking for. Oh, no, sorry. Minus 0.5. And I will use equals norm distribution. And where's my norm dist? This one here. Norm. And then I do my x. My mean is going to be 0. My standard deviation is going to be 1, and I want cumulative. I will explain you all these numbers in a minute. So let me move this and make this bigger. So what I'm looking for is the normal distribution up to the point minus 0.5. My mean is 0. My standard deviation is 1, and I want the cumulative because I want to go from minus infinite up to minus 0.5. That's what I'm trying to find. Got it? Okay, if you take a look to that, this is equal to 0.31. Makes sense to you? So now, what is this 0.31? Is from minus infinite up to the point minus 0.5. So I have a probability of equals, the probability equals minus 0.31%. No percent, 0.31. So let me go here. So according to Excel, guys, from minus infinite up to this point, this region here is 0.31. Got it? In this case, this 0.31 is exactly what I'm looking for. So the probability of C is smaller than minus 0.5. That is equal to the probability of X is smaller than 84, because I'm simply transforming this one into this one. They are exactly the same. It's going to be equal to 31%. Make sense?
Professor.
Yes.
No, yeah, I get it. I don't know if it's a dumb question. Why are we transforming it to Z again? Is there a reason? Is there something lacking in X? That's why we have to transform to Z?
You know what, now, if we have Excel, we can do this directly, but normally the process is transform to C because we have a standardized normal distribution, 0, 1. And once you have the 0, 1, you can solve everything.
Sorry?
So basically what I'm saying to you is that this process works because at the time that the procedure was not used in Excel, but at this point, really, what you can do is you simply can use Excel. You enter 84, you enter 85, that the mean, and 2. So what I'm telling you is the following. So let me remember, it's 84. So what I'm telling you is the following. So let's do with 84, okay? So what I will do from here is my norm dist, this one here. Then I enter this number, but then I need to be careful about my mean. My mean is going to be 85, correct? My standard deviation is going to be 2, I think, with example, and this one is going to be 1. Here we go. Okay, so you are basically, if you have Excel, you do it. But normally the C distribution was used because we didn't have Excel. We used to have a paper. Do you remember? I don't know if you have done this, the table, the C tables. You look the vertical with the horizontal, you cross. Okay, that's why we use the C. But indeed, in real life, you can simply do, you take this number, 85 is your mean. Don't write 0 and 1 here because it's different. And then you get the result. Make sense, guys? Okay, so let's do more examples. And I just want, you can do either method, okay? But I want you to graph. The graph must be present always. Let's do more examples. So you tell me, guys, what is the probability of X larger than 86? What is the probability of X between this one here? Yeah, and perhaps what is the probability of X larger than 84? Okay, guys, 5 minutes to do this. Okay, give me 2 minutes, guys. I will bring something. Okay, guys, I'm back. If you need some questions, if you need some help. Ready? So we do this just by Excel, okay? Much faster. You agree? Guys, you agree? Okay, so just what I'm interested is you to understand which region you're looking for. So in this case, my mean is 85, remember, for all of them, if I do the Excel method. This is 85. So we're talking about X directly. And this is 85. Okay. Now, what is important, guys, is that the region. So I want X larger than 86. So basically, I'm looking for this region here. Agree with me or not? Yes. Remember that Excel, guys, always is going to provide you the information from here to here. Always. Minus infinite up to the point. Got it? So if we do that in Excel, let me share this one here. If we do that in Excel, this is going to be 86. Do you agree? I get 0.69. Do you get 0.69? Yep. Okay, so this, what is this 0.69? This 0.69 is this part here. From minus infinite up to 86. I'm not interested about this region here. I'm interested about this region here. So this region here equals what?
1 minus it.
Exactly. It's 1 minus 0.69. So this is equal to 0.31?
Yeah.
Right? So what is this 0.31? It's simply the probability of X larger or equal than 86 equals 0.31. That is basically equal to 31%. Do you understand that? You get it? Questions? Everything is clear, guys?
Could you just go over how you put it in Excel again? Just
Yes, of course. Let me see. Give me 1 second. Excel. So let me do this one here. So I write the 86, the number that I'm looking for. So this is the C1 here. 85 is the mean of the X. X is distributed as normal mean 85, standard deviation 2. And always use 1, this cumulative, that goes from minus infinite up to this point, up to 86.
okay, perfect. Thank you.
Perfect.
Professor, so the one in Excel, the 69%, that is 86 and below.
Exactly. Exactly. And the question is not 86 or below. The question is larger than 86. Make sense, Daniel?
Yeah. So in Excel, it's always
In Excel, always from minus infinite up to the point. Always.
All right.
Right? So let's see this example.
Line negative infinity all the way until, okay.
Exactly. Negative infinity to the point that you're looking for. Okay, so let's do this example. It's going to be clear now. So this one here, I'm asking for 84 and 86, correct? So I'm going to be interested about this region here, right? Now, if you go to Excel, we already know 86. So we know that from minus infinite up to 86, this value is 0.69. Agree with me? Also, we know that from minus infinite up to 84, this is equal to 0.39, I think. That's example, 0.39.
31.
Oh, 31. So basically, this region here is equal to what? To what then, guys?
0.383.
Right, it's going to be basically 0.69, this large minus this small, correct? And so this is equal to what?
0.383.
And this one here is then my probability of X between 84 and 86. Makes sense? It's very logic. It's very simple, very logic. Makes sense to everyone? Easy? Okay, so the last one is something very similar. It's 84, and I want all this part here. I know that up to 84, I use the same numbers, is 0.31. So this part here is going to be equal to 1 minus 0.31. That is equal to 0.69. And so this should be the probability of X larger or equal than 69. Make sense? Okay, so now let's continue. 1 minute to copy.
Professor, did we talk about like in the norm distribution formula, why it's cumulative like 1 and 0?
Yeah, cumulative because I'm accumulating from minus infinite up to the point.
That's the why. Okay, and then if
Yes.
it was 0.
So 0 in Excel provides you the, I don't know, I never tried it because it gave me weird results.
Okay.
But remember, you have a discrete, if you have a discrete probability distribution, that makes sense. So you can have probability of X equals 86, for example. But in a continuous probability distribution, it doesn't make sense. It's going to give you always 0.
Mm-hmm.
Right? So it doesn't make sense to have
Right.
a 0 there. Okay. So now let's go, guys, into something that is going to basically lead us into confidence intervals. Okay, guys, take a look. I don't know if I have done that in the, well, in any case. So now imagine that we have the following. Okay, we have my population. Okay, so just focus for a minute. And then I take a sample of size n, and let's call it sample 1. Okay, then I take another sample, same size, I call sample 2. Then I take another one, same size, and perhaps another one that uses elements from both of them, etc. But the trick here is that the sample size is always n. Okay, n everywhere. Now, what I can do, guys, is from each of these samples, I can compute the mean, right? You agree with me? So if we have 10 observations, I can compute easily the mean, the average. I can do that for all the possible samples I have created in this population.
Prof?
Yep.
I'm sorry to interrupt. Kunze was kicked out of Kuzo was kicked out of class due to load shedding.
Yeah, let me see.
No, I don't think she's coming back. So there's load shedding.
Oh, what do you mean? Sorry, Kagiso. She left?
Yeah, due to load shedding. So like this, what we call load shedding here, it's like cut in power or electricity.
Oh man, yeah. Okay, it
Yeah.
doesn't matter. She will catch up here. Thank you, Kagiso.
Okay, sure.
Okay, so what I can do is I can compute from all of these guys xi, the mean. And then what we can do also is we can compute what is the expected value of, what is the probability of these means happening. Okay, so how do we call a random variable with its probability, guys? What is the name of this one here? When you have a random variable and next to each of the potential values of possible results, we assign a probability. This is called a probability distribution. Okay, please check the video that I sent you last week because I explained a lot about this probability distribution. Right? And this probability distribution, guys, has a particular name because we're talking about the mean. So it's probability distributions of the mean, of sample means. So this is the name of the probability distribution. Got it? Now, here, guys, I just need you to remember these rules. Okay, there are three rules. If X is normally distributed with parameters mu sigma, okay, so if you know that the population is distributed as a normal, the mean is also going to be normal, for sure, with parameters mu and sigma square root of n. How do we call sigma square root of n? We call it a standard error. Okay. Now, this is the first rule. You're going to make sense in a couple of minutes in examples. Two, if X is whatever, so we don't know the distribution of the population. We have no clue, okay? The parameters can be, these ones can have many, many more parameters. What is going to be the distribution of X bar? In general, guys, we have no idea. So if we have no idea, guys, we cannot find probabilities at this point. We need to have more techniques. However, if X is whatever, we have no idea what is the distribution of the population. However, if N, so the sample size is large, well, statistics says larger than 30, for me it's more than 250, then X bar is going to be normal mu sigma square root of n. So this rule here is called the central limit theorem. Okay, so by the central limit theorem, guys, if we have the sample size is large, so the sample size n here is large, we can assume that even though we don't know what is the distribution of the population, the sample mean is going to be always normally distributed with parameters mu and sigma divided by square root of n. Okay, so let's put this in perspective. Copy, and then we do examples. It's going to be clear when we do examples. Ready? Let's do examples. Okay, let's assume that X is normal 85 too. Okay, so assume that X is the grades on global financial markets. 85 is the average, 2 is the mean. Right? Assume, guys, that you have a sample of 16 people, 16 students. Okay, you randomly select from them. Well, after the COVID disappears, you go outside and you find 16 individuals, 16 students. Got it? That's what you do. You see the experiment. Now, my question is the following: what is the probability that the mean grades of these guys is larger than, let's say, 87? Got it? And then you can ask, what is the probability that the mean grade of these 16 students is between this number and this number, etc. Got it? Now, before you solve this one here, let me delete this for a minute. The technique is exactly the same as the one that we have seen, guys, before. I think I said this is 87, right? So before going from here to here, you need to do an intermediate step. You need to think, first of all, what is the distribution of X and what parameters do I have? Right? Before going here, you need to determine this part here. Well, in this case, guys, what can we say about the distribution? In which case we are?
It's normally distributed.
Yeah, so our life is solved. Do you agree? Because this one is normal, the mean is also going to be normal. So I don't care about n, it's going to be normal. Correct? Now, what are the parameters of this normal distribution? The mean is going to be the same, correct? But my standard deviation is going to be now the standard error. So this is going to be 2 divided by 16. Make sense to you guys? Once you know this one, of course, you can see this one is, this is 4, this is 1/2. So this is going to be, the standard error is going to be 0.5, correct? Now you have it, you just treat X bar like X. Once you have this information here, guys, you do as we have done before. Okay, just as a matter of practice, can you do this? Okay, 5 minutes to do that. Even less than 5 minutes. Oh, this is not X, this is X bar. Do you understand what I'm doing, right, guys? I have these 16 individuals without asking them, okay? Without asking them, what is the probability that these numbers are going to happen? That's what we're doing. Go ahead, guys. Ready? Okay, once you have the red side of the equation, guys, this piece of equation, this piece of what's that? What's that mean? Piece of cake. Okay. The thing is just to understand what you are looking for. That's all. I'm talking about not x, guys, but x bar. Okay, just remember that. My variable is not x, is x bar. So x bar has a mean of 85. Just write 85. And then the first question is larger or equal than 87. So I have 87 here. I'm interested about this part here. You agree? So let's do this in Excel. So it's, remember, I'm not using anymore this one here. I'm using this part here. So it's 85, 0.5. It is 87 here, correct? My number is 87. And then it is 85, and here I have 0.5, correct, guys? Makes sense to you? So it's basically telling me 1, 0.999997. Everyone got this number? So, oh, wait a second.
It's 1 minus that.
Yeah, exactly. So it's going to 0.99997. So this part here is going to be 1 minus 0.99997. That's basically equal to 0.00003, right? So the probability of having, in this sample of 16 people, an average larger than 87, given that I know this part here, is almost 0. Correct? Make sense to everyone?
Sorry, can you repeat the last part, the wording of it? So 0.0003.
Yeah, it is. This represents a probability that the average grades of these 16 students is larger than 87. That's what we're doing. Okay.
Wait, but I thought 85 is the average already.
What?
I thought 85 is the average already.
No. Remember, this one here is the average of the distribution. Of the population. This 85 is the mean of this one, is the mean of the average, is the mean of the mean.
Right. Mean of the mean.
Yeah, because this one here, this X bar, is a mean also.
Yeah. Yeah,
Okay.
I got confused with that. Like they're both means. So
yeah, both means, exactly. They are both means. Okay, and the intuition is very simple. So imagine that you have 16 students, okay, and you simply record that the experiment is recording the grades, okay? 82, 83, 78, 92, etc. And then from here, you compute the mean. So you simply sum and divide by 16. This is your mean.
Yeah.
Okay, so my question now is, what is the probability that this mean? So before doing the experiment, you say, okay, I have 16 students. What is the probability that the mean or the average of the grades of these 16 students is larger than 87? Right? So yeah. Basically, so that's why it's the mean of the mean. The probability that the mean of this sample mean is going to be greater than 87 is simply almost 0.0003. Okay. Okay, so now we go from 86, between 86 and 85 and 86, right? So we're looking about this part here. I know that up to 85 is what, guys?
0.5.
0.5 is exactly a half. And from here to here, well, I don't know. Let's do that. 86. So let's do Excel again. So now I have 86. I get this number. You get this number, 0.97725. Perfect. So let's do this. This part here is 0.97725. So I'm interested about this part here. Correct? So this is equal to 47 or 0.47725. And smaller than 88, obviously, is going to be almost 1, guys. You agree? So up to here is going to be a 0.999999, etc. Got it? Okay, copy for 1 minute, and then we do more exercises, and then we move into confidence intervals, guys. We are perfect.
Professor.
Daniel, yeah.
Yeah. Since people are copying, can I just ask more or less when can we estimate the midterms will be?
Yes, of course.
Yeah.
It's going to be in a couple of weeks, by the last week of March, because we are very close to where I need to be. So this class, we finish confidence intervals with one example. Next class, the first part of the class, we do something that is missing in the class, and then we are going to have half next class is going to be questions.
So
and the
is
exam
that
is going
April
to be
6th?
No, it should be the 30th.
30. Okay.
Yeah, it depends on how do you feel at 23, guys. For me, it's indifferent to do the 30 or the 6th, okay? But let's put on our calendars the 30. Okay? That was a good question. So we're going to talk more about that later later tonight. Make sense? So now let's go. Let's move. So I will do exactly the same, exactly as the previous example. X, the only thing is that I don't know if it's normally distributed. I have no idea, okay? And also it's going to be 85 too. I take a sample of 16, and my question is, what is the probability of X larger or equal than 85.5? What is the probability of X between 85.5 and 86? For example, this one. Okay.
This is a trick question because 16 is too small.
Exactly that. Do you agree, guys? So remember, before going to these ones here, you know how to do these ones here. You need to do a red stop. I need to talk about what is the distribution of this guy. Otherwise, I cannot do anything. Now, here the trick is, can I say that this is normally distributed?
No.
No, because first of all, I have no idea here, so I have no idea here. Moreover, this is case 2, right? So case 2, simply stop. This is case 2. Simply stop. I need more techniques to do this. Okay? However, in real life, guys, you know that. How do you solve this issue? You want to be able to answer this stuff. How do you solve this issue? How do you solve this one here that you have no idea what distribution is this one? Paul, you already mentioned that. What, guys?
Increase the sample size.
That's it. Bingo. Simply increase the sample size, guys. Do you agree? So in real life, let's assume instead of n 16, let's do n 100. So if n is 100, guys, what can you tell me about x bar? Even though you don't know what is the distribution
it's a
of this
normal
one here.
distribution.
Exactly. And parameters the same as before, 85 2 divided by square root of 100. So how do we call this law or theorem?
Central limit theorem.
Exactly. This is what we call case 3. And then you can solve it as before. Make sense? So in real life, guys, well, there are very strange cases in which you cannot increase n. Okay, if you cannot increase n, guys, then you are done. You cannot, better don't do anything because everything is going to be catastrophic. Okay, the best way to proceed here is, just try to increase n at least to 30. In statistics, we learn, I don't know if you have learned that also in statistics, but the magic number was 30. So if the number of observations in the sample is larger than 30, okay, you should be safe. I don't know why. In all my research, guys, 30 is nothing. You need to go at least, as I told you, 250 minimum. Or 100, yeah, you're borderline. Make sense to everyone? Okay, you can solve this later. Do you have questions? No questions? Okay, so we can move. We go to the point that, this was a reinforcement of what we have done in the previous class in the video. Okay, so you have more examples, you have more details in the video. Please take a look to the video. Now, we go to what we want to arrive. And this is the goal of the class, guys. So the only issue is that I couldn't run directly to here because I wanted to give you all the steps on how to make sense of what we're doing. This is what is called, guys, technically inferentially statistics. Inferential statistics. So what we try to do, is the following. So imagine that I have my population. Okay? From my population, I take a sample. And this sample must be representative. That's the crucial assumption of my sample. Make sense? What does this representative mean? The easy way to understand that, guys, is if imagine this is the USA income pyramid. 0.00001 are owners now of almost 20% of the total wealth. Agree? And then this is a 0.01%. And then you go to the next 5%. And then you go to the next 45%, etc. And then you go, etc. This is my pyramid. Agree? My wealth pyramid. Not income, wealth. Well, income is also similar. Do you agree? So when I take a sample, guys, if you want to analyze the wealth of USA citizens, you're not going only to take that's a sample from the richest guys in the USA, right? It doesn't make sense. You are not going to tell me that the average wealth is a couple of $1 billion of American people. That's insane. So when you do a sample, the sample must represent your population, implies that you are going to have something that looks very similar to this one here, but in small. Make sense? That's crucial. If your sample is wrong, guys, all your analysis is wrong. You agree? It doesn't matter how well your econometrics or your statistics are working. It doesn't matter. It's wrong because the input is wrong. Make sense? So that's why sampling, guys, is so important. And sometimes, no, I think most of the times we overlook at these sampling techniques. Okay? So in time, if now with this technology area, guys, one of the things I suggest you is if you can go Coursera or go any of these online classes, just take a class of sampling. in the PhD, when I did my PhD, sampling was a class for a complete year. Okay? Because it is crucial. If you don't know how to sample something, you can be making a lot of mistakes. Okay? And if you make mistakes in the data recollection side of the equation, then you're done. Everything's going to be crap. Okay, let's assume that my sample has been correctly done. And so basically what we do is we are going to find the sample mean, the sample variance, etc. Right? That's what we do. But indeed, guys, you're not interested in studying the sample. You're interested in studying the population. Here, when I talk about the wealth of my sample, I'm not interested about the wealth of my sample. I'm interested about the wealth of USA. I want to make inferences about the population. Got it? So what I'm trying to do is I'm trying to make sense of what is the population mean, what is the population variance, for example. So going from here to here is called inferential statistics. It's basically we do educated guesses based on statistics, sample statistics. We want to make educated guesses about the population parameters. Make sense? And of course, for that, one ingredient that is crucial are the probabilities. Okay, so now we have everything. So we know how to do this, we know the probabilities, now we can jump into inferential statistics. Ready? Make sense to you? Okay, so now let's go into point estimates. Point estimates, guys, are simply, what is the point estimate of mu? The population mean. The point estimate is the sample mean. What is the point estimate of the population variance? The point estimate of population variance is the sample variance. Remember, guys, that the sample variance, the formula, is always divided by n minus 1, not by n minus 1. What is the sample mean? Is simply the sum of xi divided by n. Okay, the simple average. Ready? Make sense? Okay, so point estimates. There are other estimates that are called confidence intervals. Do you understand, guys, that it's so tricky trying to say that, you know what, my sample mean is equal to the sample population mean? It's very tricky. Do you agree? Got it? Because imagine, I don't know how, God provides you with an illumination, and you know that this is the real population mean. Okay, the real population mean, guys, is known if and only if you do the census, correct? Because the census includes everyone in the population. In that case, the sample population is exactly the sample population because you're taking every single individual in your sample, in your population. However, guys, when we do a sample, okay, so even though it's a very large sample, what can happen is a bunch of things. You can be very lucky and your sample mean is exactly the same as your population mean. Do you agree? But you're lucky. Another situation can be that, you know what, you're not so lucky and perhaps you overshoot your mean. Or perhaps you undershoot your mean. Or any possible combination. Do you agree with me, guys? So you have no idea, indeed, where my population mean is with respect to my sample means. And that's a tricky part here. So what do you do then, guys, in order to be protected against having a single number? Okay, let me give you the following example. Okay. Follow me for a couple of minutes, guys. Okay, copy and then follow me. So you are going to understand what I'm talking about. Are you ready, guys? Okay. So please follow me for a minute. Let me tell you the following example. Imagine, guys, you're going to work for me, okay? And what I will do is I will give you 10 years of data, revenues, the last 10 years of revenues. And assume that these last 10 years of revenues, the average of this one here, the mean of these 10 years is equal to $10 million. Got it? And then as soon as you're going to work for me, I tell you the following. Guys, tell me your best estimate for next year, okay? And the only condition that I provide you is that if you really make what you told me, I will give you a bonus. Otherwise, you're going to be fired. Make sense to you? Okay, guys, give me your forecast for next year. So you have 10 years of data, revenues, and the average of these 10 years is $10 million. What is your best estimate? Knowing that I will evaluate you at the end of the year, and if you don't achieve what you have told me, you're going to be fired. But if you achieve what you told me, you're going to have a very beautiful bonus. So give me a number or whatever. Come on, guys. Why not someone is jumping to the pool immediately? Someone can tell me $10 million, or perhaps, you know what? Yeah, perhaps there is some growth, perhaps $11 million, or perhaps $9 million. Why don't you give me these numbers?
You want to give it as a confidence interval so that you don't get fired?
Yeah, well, you know what the risk, exactly that. The risk of giving me a number is that you don't feel confident. Agree with me or not? So if you give me $10 million, okay, we arrive December 31st, and you got $9 million, 999, I can still fire you because you told me 10. It's not 999, so you're fired. Do you agree? So, wow, yeah, of course, I don't feel confident about that. So what you are going to do is you're going to give me a confidence, you're going to give me an interval. Do you agree? Okay, give me an interval. Just guess, because you don't have, yeah.
Between 9 and 11.
Yeah, well, that's a logic one. They agree between 9 and 11. So for me, it's going to, as an owner, it's going to be, yeah, it's logic, 9 and 11, good. So you feel more confident, right? Kaiso, you're not like having 10, because if you are between 9 and 11, you're more protected. Make sense to everyone? Now, guys, what is the most protective, or when do you feel 100% confident that you are never going to be fired, or your result is going to be always in that interval? Between what and what?
0 to infinity.
No, not necessarily. It can be minus infinity to plus infinity. Do you agree? Because you can lose also. So you're going to be completely secure when you go from minus infinity to plus infinity. Unfortunately, guys, that information is useless. So if you tell me that, I fire you now. I don't wait until December. Makes sense to you? Because you're giving me something that is stupid. Makes sense to you guys? Okay, so building confidence, building intervals is what we're going to be working on now. So what we are going to try to do now, guys, is always, it's going to be centered around your sample mean. And I will show you the ways of building confidence intervals, okay? So why they are called confidence intervals? Because we're going to use a confidence level, okay? How confident you are going to be by giving me this interval, got it? So that's what we're going to be doing in a minute. Make sense to everyone? Okay. Copy and then I can move. Okay. So let's do the following. Let's do case one. Confidence intervals if we know population variance. Well, population standard deviation. Okay. My population mean, guys, is going to belong to an interval that is centered around X bar plus minus Z sigma square root of n. This is going to be my formula. Now take a look to my formula, guys. I know X bar, I know sigma because by assumption, and I know n, my sample size. What is the only unknown? This Z value, correct? And this Z value, guys, depends on something that is called the confidence level. And the confidence level, guys, that the levels that we always use is 90% or 0.9. Yeah, let's do 0.9. It's going to be 0.9, the common ones, 0.95, and 0.99. Okay, so these are the confidence intervals, the confidence levels that we always use, guys. No one is going to complain about that. In order to understand, let's do one example. You're going to see how easy this works. For example, let's assume that I have a sample of 100 individuals. Let's assume that a sample grade equals 87. Let's assume that sigma, so this is assumption, that sigma equals 5. Okay. What I want you to tell me is, oh, for a confidence level of 90%, I want you to tell me mu belongs to what and what. Okay. Copy and we do this together, and then you do a couple of other examples. Okay, ready, guys? So let's do this together. And once you see this example, you're gonna see how easy this works. Okay, so the first thing we need to do, guys, is we need to graph, okay? Because if you see in the formula, I have X bar, I have sigma, I have N. The only thing that is missing is Z. Okay, so how this works? So this is my normal distribution. And I want this to be equal to 90%. So this implies, sorry, there is another term here that is called significance level. And significance level, guys, is simply equal to 1 minus the confidence level. And the significance level is called alpha. Okay, so if its confidence level is 90%, the significance level is 10%. If the confidence level is 99%, the significance level is 1%. Right? It's simply 1 minus this number. So this one here is going to be alpha over 2. So if this is 90, this is going to be 0.05. And this is also alpha over 2 is going to be 0.05. Agree with me, guys? Agree? So what is missing? This is the C value. As soon as this is symmetric, is equal. If this is C, this is the negative of that, minus C. How do we find these critical values? Please follow me for a minute. We go to Excel. Oh, where's my mouse? Let me show you Excel. Where's my Excel? These ones here were critical values, correct? Now what I'm interested is finding probabilities. So what I will do is what is my C is 0.9, 0.05. Okay, let's write the alpha over 2, 0.05. And what I will do is I need the norm inf, this one here, of this one, comma, 0, comma, 1. Let me see, yes. So what I do is I divide, I do the alpha over 2, 0.05 in this case. And my mean is 0 and my standard deviation is 1. Do you understand? Okay, so what is this 1 point? Give me 1 second, guys. Okay, so this 1.6645, okay? That's the number that we normally use, is this number here. This number here equals 1.645, and this number here equals minus 1.645. You agree? Now, guys, we have everything. Everything. You can see. So based on this, I will say that mu belongs to, my mean is 87, plus minus 1.645, that multiplies 5 divided by square root of 100. Correct? We have all the numbers, so we simply compute the numbers and you give me the lowest value goes to the left and the largest value goes to the right. Okay. Where's my calculator? Okay. So you correct me, guys. I get here 87.8225. And 86.1775. I need to verify. Yeah, I need you to verify this, please.
I got the same.
Beautiful. Okay. So basically, guys, this means the following. At a 90% confidence level, I believe that the grades, the mean grades for all the students are going to be between 86.17 and 87.22. Make sense to you guys? Okay, so now you continue with examples. The same data. So I have the example 2. The only thing that I'm changing here, guys, is my confidence level equals 0.95. My confidence level 0.99. My confidence level 0. My confidence level equals 100. Very quick, guys, please. Quickly. Oh, it's 909, guys. I need to run. Can you tell me what is the 95? So alpha over 2 is going to be 0.025, correct?
I got negative 1.96.
Yeah, 1 second. 1 second, guys. Okay, so you get what?
1.96.
Yes, 1.96. I need you to confirm, guys. Anyone else? You get this?
Yep.
Perfect. Now, what happens when it's 0.005?
$2.576.
Confirm.
Perfect. Agree?
Professor, so just to clarify, so we're saying is at in a 99% confidence level, the mean would be the mean, right?
Yes.
Would be between 85.712 and 88.288.
Yes. This
Is
is
that the wording correct?
this is the population mean. The population mean. It's the population mean.
Okay.
Okay. So here, basically, guys, this is going to be basically 87 plus minus 1.96 that multiplies 5 square root of 100. You agree? And this one is going to be mu belongs to, please, if you can help me with estimating these numbers, 2.5765 square root of 100.
The first one's plus or minus 0.98, and the second one is
Wait,
plus or
wait,
minus
wait.
1.288.
Yep, give me 1 second. Tell me, please tell me. So this one here, so this one here is mu belongs to what? What number?
Plus or minus 0.98. 87 plus or minus 0.98.
Yeah, can you give me the numbers?
Oh, 86.02 and 87.98.
Perfect. Someone to confirm, so we have values.
Confirm.
Perfect. And this one here is going to belong to what?
I got 85.712 and 88.288.
Okay. So first thing that you need to note here, guys, is that the more confident you want to be, the wider the intervals. You see? 95 is more confident. So this is wider than this one here. And then if you want to be more confident, this one here is wider than the other two. Make sense? It is very logical. More confidence, larger the interval. Agree with me, guys, or not? Yep. Okay.
Yeah.
Now, what happens if the confidence level is 0, guys? So the confidence level 0 implies that we look for Z at this point here. And at this point here, what is the Z? 0. Correct? So this implies that mu belongs to 85 plus minus 0 that multiplies 5 square root of 100. So basically mu is equal to 85 and this is equal to X bar, the point estimate. Remember when I was telling to you how confident you feel when you give me a number? 0. You agree? 0, guys. Now, what is that extreme confidence? Of course, 100%. You agree? Yeah, but 100% means a C value of what? Minus infinite or plus infinite. Agree? Because the C should be somewhere in the infinite. So here, mu is going to belong to 85 plus minus infinity 5 divided by 100. So basically, mu belongs to minus infinity plus infinity. useless. Got it? Questions, guys? I think we stop here. We have done what we should have done. We we were supposed to do. So next class, we use half class to finish what we need to finish, and then we're going to be ready. What I will do, guys, is I will prepare some notes, kind of an exercise that is going to prepare us for the exam. Guys, so I will send this to you by Friday. Please, if I don't send you anything by Friday, send me an email, because I should have forgotten. And then I will send this to you. So during the next class, guys, you solve everything except a part that I will tell you. You are not going to be able to solve this exercise. Okay, so you solve everything that is going to be based on everything we have done in the past, that is going to be covered in the exam, except one part that we're going to do together on next class, next Tuesday. Got it?
Sorry, and what day did you say the exam was going to be?
On the 30, and if I see that you are lost next class, we can do this on the 6th. Okay. You know, I'm flexible. The things that you learn, guys, and all this stuff is very crucial for global trade. Okay, make sense? Okay, guys, have a good night and see you in a week then. Take care.
Thank you, Prof.
Thank you,
My pleasure.
Professor.
See you guys. Take care.